Welcome back to The Explainer. I am absolutely thrilled you're here today because honestly, we have a really fascinating code analysis to unpack. Think of today's source material not just as a standard run-of-the-mill programming exercise, but more like an intricate technical puzzle. It's almost like a digital heist, where we have to navigate this maze of incredibly strict constraints to get the exact output we need. Now, if you've ever coded in languages like Python or JavaScript, you might be used to playing fast and loose with data types. But today, we're looking at Go. And Go is notorious for being uncompromisingly strict, so we really have to be incredibly precise to pull this off.
So here's the real crux of our challenge. How exactly do you generate nearly 5,000 unique number pairs without setting off the alarms of Go's strictest rules? To be precise, the output requires 4,950 unique pairs. And that isn't just some random number we pulled out of thin air, it's the exact mathematical combination of 100 items taken two at a time. Trying to brute force this math with messy, overlapping code? Yeah, that will instantly trigger the security system. In this specific case, the 01edu strict checker acts exactly like that alarm, treating your common programming shortcuts as completely illegal operations. It's a trap, for sure, and we have to cleverly bypass it using highly structured, mathematically sound programming logic.
All right, let's dive into this. Here is our game plan. First, the challenge. Second, the type mixing trap. Third, generating unique pairs. Fourth, extracting digits. And finally, number 5, the final output.
Let's kick things off with part 1, the challenge.
The goal outlined in our source material is incredibly specific. We need to print all possible combinations of two different two-digit numbers. They have to be in ascending order, starting from 0001 and going all the way up to 9899. But the real constraint here is visual. It's not just about generating the numbers internally. It's the fact that they must be printed on a single continuous stream of data. Literally, one single line separated perfectly by a comma and a space without a single misplaced character ruining the formatting.
Now, before we write any logic, we just need to make sure we're on the same page with our terminology. In Go, the language this exercise is built for, we are dealing with what are called runes. A rune is basically just a single Unicode character. Go uses runes to handle complex Unicode characters globally. This means it treats the number 0, written out as a character in single quotes, as a purely visual character representation, not as a mathematical 0. Because our output requires us to print these exact characters to the screen, understanding this distinction is absolutely crucial. It's the key to our entire solution and, frankly, it's exactly where the danger lies.
Which brings us right to part 2, the type mixing trap.
This right here is a massive focus area for us today, and it explains why so many initial attempts at this exercise just flat out fail. A very common, kind of naive approach is to try and compute the character codes mathematically. A programmer coming from a dynamic language might just take the character 0 and try adding an integer variable I to it, expecting the language to just sort of magically figure it out. But remember, Go relies on strict static typing. Its strict checker is specifically designed to prevent unintended, dangerous behavior in computer memory. In Go, 0 is an untyped rune constant. Adding a raw integer variable to it, that causes implicit type mixing. The checker instantly flags this as an illegal call, throwing a harsh error and stopping your program dead in its tracks. No way around it.
So how do we get around it? Notice the array on the right acting as our safe harbor. By defining an array called digits that explicitly stores the 10 numeric characters as individual, legal rune values, we basically create a foolproof lookup table. By mapping integer indices directly to these pre-stored character runes, we completely bypass computation. We aren't doing any math on the characters at all. We are just using safe, plain integer arithmetic to point at a spot in a list and grab what's already there. It's clean, it's memory safe, and it perfectly avoids the illegal operations that trip up that strict checker. It's a real game changer.
Moving right along to part 3, generating unique pairs.
With our characters safely accessible, let's look closely at how nested loops actually generate these unique pairs. We use 2 loops working in perfect tandem. Think of it like this. Imagine the outer loop, I, is the hour hand on a clock, and the inner loop, J, is the minute hand. The outer loop runs from 0 to 98. When I sits at 0, J sweeps all the way from 1 up to 99. Then I ticks forward to 1. But crucially, and this is the secret sauce, J doesn't restart at 0. Because J is strictly defined in the code as I plus 1, it starts at 2. This continuous offset acts as a powerful mathematical ratchet. It ensures we only ever move forward, completely eliminating duplicates and preventing reverse pairs like 0100 from ever showing up. This algorithmic efficiency is what guarantees we hit exactly 4,950 unique ascending pairs. Let's jump into part 4, extracting digits.
Let's bring this to life and make it concrete. Imagine the program is holding the raw integer 47 in memory right now. Our beautiful nested loops have generated this number, but the code still only knows it as a single, solid, raw integer. We need to print a character 4 and then a character 7. So how do we split a solid number into individual pieces? Well, we use math like a pair of precision tweezers. Step 1 is integer division. Because we operate in a base 10 number system, dividing 47 by 10 gives us exactly 4. Remember, integer division simply chops off the decimal. That extracts our tens digit perfectly. Step 2 is the modulo operation, which gives us the remainder of a division. Why does this work? Because any number modulo 10 always naturally isolates the rightmost digit. 47 modulo 10 leaves us with a remainder of 7, boom, our units digit. This is one of those brilliant little aha moments in computer science. We then take that 4 and that 7, plug them right back in as indices into our safe harbor lookup array, and safely fetch the exact rune characters we need to print.
Finally, part 5, the final output.
We are in the final stretch now. Take a real close look at how we solve the trailing comma problem. It's an incredibly elegant use of conditional logic. The instructions demand a comma and a space between pairs, right? But the very end of the output stream must have a clean new line, not an ugly dangling comma. Missing this tiny visual detail is actually the most common reason the o1.edu automated checker fails a student's code. It's brutal, but by adding a simple if-else conditional statement, we just check if our hour hand, I, is exactly 98, and our minute hand, J, is exactly 99. If it is the final pair, we cleanly print a new line character. For every single pair before it, we just print the standard comma and space.
Okay, let's see how the whole shebang builds into a complete bulletproof solution. First, we used a lookup array to definitively sidestep that illegal type mixing. That was absolutely crucial. Second, we used nested loops with a mathematical ratchet to guarantee unique ascending pairs. Third, we leveraged base 10 division and modulo to safely extract our digits like tweezers. And finally, we used simple conditional logic to nail the formatting constraint. What you've just learned isn't just some parlor trick to pass a coding test. By walking through this, you've really learned how to respect strict memory types, choreograph data safely without overlap, and format a continuous data stream perfectly. Honestly, these are the absolute hallmarks of a secure, algorithmic, and production-ready developer.
Once you see the underlying structure here, you realize just how powerful these concepts truly are. So I want to leave you with a final thought to ponder. If we used an inner loop starting at I+1 to guarantee 2 unique digits, how would you apply that exact same structural logic to write a third loop for 3 unique digits? Think about it. Keep building on these robust foundations, and I'll see you in the next explainer.